This is lesson 6.3, the fundamental theorem of calculus. Students will use parts 1 and 2 of the fundamental theorem of calculus, interpret the integral of a rate of change, and interpret the integral as an accumulation function. So this is the most important part of the second half of calculus here. So we've been talking about antiderivatives and integrals. This is how do we calculate things. So we've already said that an integral can calculate the area under a curve for us. So now we're going to apply that to different functions, different areas, and different scenarios. So the first thing I have for you is the fundamental theorem of calculus part 1. Our textbook calls it part 1. Some other places call it part 1. Just a little note, some resources call this part 2. Namely, my last textbook used to call this one part 2, but this textbook calls it part 1, so we're just going to roll with it. Suppose f is a function that is continuous on a closed interval from a to b. The function I is defined by the integral from a to x of f of t dt. It has the properties that it's continuous on the interval from a to b and differentiable on the interval from a to b. Moreover, the derivative of that integral will be equal to the original function for all of x from a to b. There's a lot going on there. So what's going to happen is the derivative undoes the integral, just like adding undoes subtraction and multiplying undoes division. That derivative will undo the integral. And so what changes is this t gets replaced with whatever variable is up here. And in that first example, it's x. And you are left with only that inside piece, but you've now replaced any of the t variables with an x. So what does this mean for us? It means you don't actually have to find the antiderivative. You don't actually have to find the antiderivative. So say I had a number 7. I timesed it by 2. That's 14. And then if I take 14 and divide by, I choose a bad number that only has 2 factors here. If I take 14 and divide by 6, I've got 16 over 4. Nope, I don't. I've got 14 over 6. So if I take that 14 over 6 and undo it, so 14 over 6, instead of dividing by 6, I'm going to multiply by 6. I now have 14, and instead of timesing by 2, if I divide by 2, we get back to where we started. So the same thing is happening with the derivative and the integral here. So I'm going to do this a little bit backwards. I'm going to show you what the answer is, and then on the next page, I'll show you why it works or why that happens. So for example 1, we want to find each of the following, the derivative of the integral. Well, if I'm finding the derivative of the integral, they essentially cancel one another out. And I'm going to rewrite this as the square root of x plus 1. I know it feels wrong. I know it feels like you didn't do enough math. I know all of those things. But you have to imagine in your head, we found the antiderivative of whatever this is. Then we found the derivative of that antiderivative. So if I found the derivative of the antiderivative, I'm back to where I started. I've just replaced the t with an x. I know it feels weird. Letter B, same thing. If I were to find the antiderivative of this, and by the way, we don't have skills to do that right now, and then find the derivative of that antiderivative, my final answer, lost in your bud, is going to be x cubed minus 1 over 2x squared plus x plus 1. You don't have to do anything else. There's no quotient rule. There's no actual antiderivative. You are just replacing that s variable in this situation with that x variable. So all the s's are replaced with x. Does it matter what the 2 is? Nope, it doesn't. Now, that's great if I have just an x, but what happens if I have something more complicated than x? You know, the x to the first power. When we've been doing u substitution, you've been asking me, I guess we haven't done u substitution yet. You've been asking me, how do I know what u is? And that was true when we did the chain rule. So because this is more than just x to the first, this requires a chain rule. So we're going to do what we did above, exactly the same thing. Replace t, both t's, with this 3x squared plus 1, and then there's one more step. So this is e to the 3x, I said squared, but it's cubed plus 1, plus 3x cubed plus 1. And then here's the radical. So that's the replacing piece. Now, because, again, this is more complicated up here than just x, we need to follow it up with the derivative of that quantity. So the derivative of 3x cubed plus 1 is 9x squared. Now, this looks a little sloppy, and it is. There's not really anything else you can do with it. I might put the 9x squared in the front of the radical so that if I'm in a rush, I don't get lost there. Something like that. There you go. Now, example 3 is similar to example 2 in that, again, I have this limit, this boundary of integration that's more than just x to the first. So I know there's going to be a chain rule. But the other difference is it's sitting in the bottom. So that's going to change our answer just a little bit. We're still going to replace t with the x cubed. So this becomes x cubed to the 4th plus 1 to the 1/3. So what's that new thing? We need the derivative of that x cubed, which is 3x squared. Here's the new thing I have to worry about. Because this is in the bottom, my answer is going to be negative. So if I just tidy this up a little bit, I'll have the negative in the front, 3x squared, x third to the 4th, those get multiplied. So this is x to the 12th plus 1, the entire quantity to the 1/3. All right, so why does that work? Why does that work? So let's look on the next page. The fundamental theorem of calculus part 2, and I think that this will sit with you a little bit better. The fundamental theorem of calculus part 2. So again, some resources call this part 1. So one of these days, I'm going to have to do a little bit of research and figure out which one wins or if it doesn't matter or whatever the case is. So this is the one that we're actually going to use more often, and I think this will make more sense. Suppose f is a function that's continuous on a closed interval from a to b. If f, capital F, is any antiderivative of the function on the interval from a to b, then the integral from a to b of f of x dx is the antiderivative evaluated at b minus the antiderivative evaluated at a. So before we jump into example 4, these should go on your golden ticket. These will go on the back. Let's talk about a couple of these rules. So the power rule, just to remind you, is x to the n plus 1 over n plus 1. Don't forget your plus c. E to the x stays as e to the x plus c. 1 over x is natural log. You really should have absolute value of x plus c. Sine came from cosine of x plus c, but it's going to be negative. Cosine came from a positive sine of x plus c, and secant squared came from tangent of x plus c. So again, those are, the antiderivatives. Those are the backwards of the derivatives. I'm giving you the answer. You tell me the question. So part 2 of the fundamental theorem of calculus here. You got to know how to do it. You have to know how to do it well. But if you take your time, it's really not too bad. If I have x squared, the antiderivative I know is x to the 3rd over 3. We know that there's a plus c there. But we're now going to drop the integral sign. We're going to put in those brackets and slide our upper and lower boundaries to the right-hand side. So we have the antiderivative, we have the two boundaries. Remember, the top one is b, the lower one is a. You're going to replace x with those numbers. So this becomes 1 cubed over 3 plus c minus negative 2 cubed over 3 plus c. So I've got 1/3 plus c minus, this is going to be -8/3 plus c. Now, if I take that negative or that minus sign in the middle and distribute it, I have 1/3 plus c plus 8/3 minus c. Now, plus and minus c, what's going to happen with those? They're going to cancel. That's going to happen every single time. So because of that, we don't really worry about writing plus c up here. We know it's just going to disappear. C minus c, a constant minus a constant, is gone. So we are just going to be left with the variable terms. Just good to know. So if we come back to our final answer, 1/3 plus 8/3 is 9/3, which we know is 3. Now, in the last lesson, we practiced using Math 9 in our calculator. You could check your work with Math 9. These are kind of nice. You can go through and do them by hand. You can also check your work. So let's look at letter B. I see a trig function. We just wrote up above cosine. Where did cosine come from? Cosine came from sine of x. This is called a definite integral because it has boundaries. I'm not going to worry about the plus c. This is between 0 and pi/6. So what do? I have sine of pi/6 minus the sine of 0. So on that unit circle, you know where pi/6 is, the sine value is the y value. That's going to be 1/2. Sine of 0 is 0. So my final answer is 1/2. And again, you can check your work with Math 9. It's kind of helpful. Letter C, this one's kind of wacky. This is one of the special ones. If you look on the derivative side, there is one that has this as an answer, and that's inverse sine. Let me call it, do this. Inverse sine of x, we're going to evaluate between 0 and √3/2. So this is the inverse sine of √3/2 minus the inverse sine of 0. So to remind you, how do we evaluate this? Inverse sine of theta. Nope, I did that wrong. It's too early in the morning. Inverse sine of your number is equal to the angle. So in here, this is the ratio. That's the √3/2. That's the 1/2. That's the 0. That's the 1. So this is inverse sine of 3/2. √3/2 equals what? So what I'm really saying is the sine of what angle is equal to √3/2. Sine, I know, is the y-coordinate. So where's the y-coordinate equal to √3/2? That happens at pi/3. Yes, it also happens at 2 pi/3, but inverse sine has to be in quadrant 1 or quadrant 4, not quadrant 2. So that's how I know it's pi/3. Inverse sine of 0 is actually 0, so my final answer is pi/3. Now, if you go to check that in your calculator, obviously we don't get radical or radian answers back, so you will have a crazy decimal. It'll be a little bit bigger than 1. You could just take pi, divide by 3, and make sure you get the same crazy decimal. That's all. Letter D. We are looking for the antiderivative of 1/x. I know that's natural log of the absolute value of x between 1 and 2. So natural log of 2 minus natural log of 1. Yes, absolute value is there, but they're already positive, so then you can kind of just drop them out. So natural log of 2 minus natural log of 1. What do we know the natural log of 1 is the same thing as? We know that's 0. So my final answer is natural log of 2. Good. Example 5, find the area under the curve of e to the x from -1 to 1. So if integrals calculate the area under a curve, all you have to do is set this up. So here's my integral from -1 to 1, e to the x dx. The antiderivative is e to the x. I know we're going to evaluate between -1 and 1. So this is e to the 1 minus e to the -1. You don't like negative exponents, so I'd call this e minus 1 over e. You could go through and find a common denominator of e, but it's not necessary. So there you go, fundamental theorem of calculus. part 1 or part 2, depending on your resource. But for our textbook, this is Fundamental Theorem of Calculus, part 2. All right, now, if I take this idea and apply it to a word problem or a real life situation, what does that look like? I know we get a little cringy at that phrase word problems in math. I think we were all traumatized in late elementary school, but these are honestly the nicest real life scenarios that we have in this class. Usually what happens is we give you a rate and you have to integrate it. So we're looking at the net change. So net change as the integral of rate. The net change in s of t position over an interval t1 to t2 is given by the following integral. And don't lose sight of this. This is s prime. Just as a reminder, s prime is the same thing as velocity. So if I integrate that velocity, I wind up with position at time 2 minus position at time 1. So that is the change in position. It won't tell you exactly where it was unless you have a starting location, but it can tell you how far it moved. So example 6, a particle moves along the x-axis so that any time t, its velocity is given below, where t is measured in seconds and v of t is measured in meters per second. Find the integral from 0 to 5 of v of t. Well, that's straightforward enough. So we'll set up the integral 0 to 5. 6t squared minus 2t plus 1. You technically need a dt on the end. So now we're going to find the antiderivative. So this would be 6t to the third over 3 minus 2t squared over 2 plus t, not x, because we're dealing with t variable. You don't need the plus c. These are my boundaries, 0 and 5. So by the fundamental theorem of calculus, what do we do next? We're going to put in those boundaries. Which one do we put in first? The top. I always put the top one in first. So this, I'm going to kind of simplify at the same time. This is 2, 5 cubed minus 5 squared plus 5 minus, now if I put 0 in for all 3 of those all become 0. So what do we have here? 5 cubed is 125 times 2, this is 250, minus 25 plus 5, so 225, 230. So I have 230 is my numeric answer. Parts B and C want us to figure out what that really means. Using correct units, interpret that integral in the context of the problem. So 230, I'm going to come back up here to my units. I know if it's in meters per second, when I integrate, I drop that per second, I drop the per time. When you find the derivative, which is the rate of change, you add in that per second, per hour, per minute. You add in that time element. When we integrate, we undo that time element. So this is 230 meters. Now, great, 230 meters, but we need to reference those times. We need to talk about 0 and 5, because if I do this whole problem again, between 10 and 15, I'm going to have a different answer. So you need to make sure that we're talking about 230 meters. This would technically be displacement, not total distance traveled. 230 meters displaced from time equals 0 to time equals 5. That works. If at t equals 0, the particle was x equals 2, what is the position of the particle at t equals 5? So we figured out how far it's moved between t equals 0 and t equals 5, and that's the 230 we have above. So now we have to talk about this initial piece. And yes, you're going to add a 2. However, these problems get more complicated. I want you to feel comfortable with the notation. I would say the position at 0 plus that change in position from 0 to 5 is how you're going to put this all together. So get comfortable with this. Make sure you know how to write this, because you're not always going to start at time 0. You're not always going to have a nice little 2 in the beginning. These get more complicated. These problems are going to get more complicated. So you want to take s of 0, which we know is 2, plus the value of the integral, which we found up above is 230. So we have 232 meters at t equals 5. So that's not how far it moved, but that's its actual location now. If we know where it started, we can know where it ended. Awesome. Example 7, the marginal profit, which is P prime in dollars per unit for producing and selling X units of product, is given by the square root of X. Suppose 100 units have been produced and sold. Find the additional profit from producing and selling 21 more units. If you've ever made anything and sold it, you know it's very expensive to do that first one. If you're doing t-shirts, or if you're really good at making something, you have to get the supplies, you have to get the machine that's going to print your t-shirts or do screen printing or the Cricut or whatever else you have to get all those pieces initially. So that first one is very, very expensive, but the more you make, you don't have to rebuy all the equipment. So the cost of producing additional items goes down until you have to buy another machine or something like that. It's oversimplifying the process, but you get the idea. So the marginal profit is square root of X. That is going to go inside of our integral. Our boundaries are going to go from 100 to 21 more. So this is 100 to 121, and this is a dx problem. Great. I know that the square root of X is the same thing as X to the 1/2. So I'm going to integrate X to the 1/2. This is X to the 3/2. Dividing by 3/2 is the same thing as multiplying by 2/3 between 100 and 121. So we have 2/3 121 to the 3/2 minus 2/3 100 to the 3/2. So 2/3 square root of 121 is 11 cubed minus 2/3. This was 100 cubed, or 10 cubed rather. What do we got? 2/3 11 cubed minus 10 cubed, whatever this works out to be. I don't have a calculator right in front of me, and I can't do 11 cubed this morning. But that would be the dollars. That's how many more dollars you've earned for items 100 through 121. Okay, excellent. Now, velocity, position, acceleration. We know that these are themes that keep coming up in this course. So I know you might have some physics ways to solve these, but remember, I'm looking for calculus equations. The acceleration of an object in rectilinear motion, that just means straight line motion, is given by the acceleration function is 10 times e to the t meters per second squared, where t is greater than or equal to 0 and the time is in seconds. If the initial velocity is 150, what is the velocity at time t? So if we have acceleration, how do I get to velocity? Well, if you integrate acceleration, that's the same thing as velocity. So we are going to integrate 10e to the t dt. I don't have boundaries. This one's going to be an indefinite integral. So this is 10e to the t plus c. And I should say that this is equal to velocity. So velocity is 10e to the t plus c. You've already done initial value problems in the last unit. So if I know that v of 0 is 150, I'm going to say that 150 equals 10 e of 0 plus c. Just watch your e to the 0 power. A lot of times we like to say, oh, look, 0, the whole thing's 0. But remember, 0 is an exponent, means 1. So this is 150 equals 10 times 1 plus c. C is equal to 140. So if I put all this together, our velocity is 10e to the t plus 140. So that's our velocity equation at times t. Just means we've got a t variable. Maybe you like that a little bit better. Okay, if the initial position, and initial means time 0, if the initial position is 0, then what is the position of the object at t equals 2? So we're going to do this again. So now we have to integrate velocity, and that will get us to position. So integrate 10e to the t plus 140 dt. The antiderivative of 10e to the t is 10e to the t. 140, we need to put a t on it. And there is a plus c. And I know that this is our position function. Sometimes we use s, sometimes we use x. So the initial position is 0. So I'm going to say, all right, position is 0, time is 0. So 0 equals 10 plus 0 plus c. So c is equal to negative 10. So the position function is s of t equals 10e to the t plus 140 t minus 10. So now if we want to find the position at t equals 2, what do we do with that t equals 2? We put it into for t. S of 2 is 10e squared plus 140 times 2 minus 10. You don't have to give me a decimal equivalent. Anytime you type the letter E in your calculator, you've automatically rounded it and it's less accurate than just the letter E. So the letter E is totally fine. 140 times 2 is 280. 280 minus 10 is 270. So that is where the object is at t equals 2. All right. Now, definite integrals calculate signed area. What do I mean by that? I mean that we can have positive and negative areas. So positive and negative areas. So above the x-axis, positive area. This is negative area. This is positive area. So we can take into account direction when we're dealing with integrals. Use the graph of f of t equals sine of t to find those values. Now, the picture above does not relate to number 9. It is the graph of the sine of x. And if you want to look at this, it might help. Sine of x passes through the origin. One wavelength is 2 pi. This is pi. So for example 9, we are looking at the graph of sine of t. Now, there's a piece of information missing, and that's where to start the problem. They didn't actually come through and tell us. So just on the side here, just tell me that 0 is less than or equal to t, which is less than or equal to 2 pi. So let's just stay in this first wavelength. And we know it goes to 2 pi, but they didn't actually say it starts at 0, so we want to say it starts at 0. What we're going to do is set up the integral between 0 and x. So between 0 and x. So this is kind of the bridge between the fundamental theorem of calculus part 2 and the fundamental theorem of calculus part 1. We're going to set up our own problem. So inside of there, we'll put the sine of t. You can't use x or t in both places. They have to be different variables. Otherwise, you wind up in a mathematical loop that you can't get out of. So 0 to x sine of t dt. So I know that the antiderivative of sine is negative cosine of t. This is between 0 and x. So I'm going to put in the x, negative cosine of x, minus negative cosine of 0. Negative cosine of x has to stay that way. So this is area, by the way, area. I think our, the little box with the theorem called an I, that's fine. So negative cosine of x, cosine of 0 is 1, so this is really plus 1. So what I have is this formula that will calculate these 4 things. So I don't have to find this antiderivative 4 times over and do fundamental theorem of calculus 4 times over. I can just do it once, and now I substitute things in. So they're going with f, so let's go with f. So if I want f of pi over 2, that is negative cosine of pi over 2 plus 1. We'll come back and figure that out. And f of pi would be negative cosine of pi plus 1. And f of 3 pi over 2 is negative cosine of 3 pi over 2 plus 1. And finally, f of 2 pi is negative cosine of 2 pi plus 1. So altogether, let's go through and figure out what these are. That's a lot of red. It's looking a little aggressive. F of pi over 2 Cosine of pi over 2, that's at the top of the unit circle. Cosine value is 0. 0 plus 1 is 1. F of pi, cosine of pi is -1. Negative of the -1 is +1 plus 1 is 2. 3 pi over 2 is at the bottom of the unit circle. Your cosine coordinate is 0. 0 plus 1 is 1. And 2 pi is all the way to the right. That has a value of 1. So -1 plus 1 is 0. There you go. So what we've basically done is said, okay, where's x? Here's x. And we can move x. And wherever we decide x is, these 4 places on the bottom, that will calculate for us the area. Now, I promised that I would loop this back around to that fundamental theorem of calculus part 1 at the beginning. Here it is. If I take my formula, capital F of x is equal to negative cosine of x plus 1. If I find the derivative of that, the derivative of cosine is negative sine. So this will be sine of x. The derivative of 1 is 0. I wound up back where I started. So instead of sine of t, I have sine of x. So that's how they wind up to be the same thing. Why we don't have to worry about the constant is the derivative of any constant anywhere is 0. So that's why it didn't matter back at the beginning. Back at the beginning, we didn't worry about the 0 or the 2 or the 4 or the 5 because those wind up to be a constant. The derivative of a constant is 0. So good luck with assignment 6.4. Let me know if you have questions.